Welcome back, everyone. In this video, we're going to finish looking at determining molecular geometries, and then we're also going to look at the effect of multiple bonds on bond angles and evaluate cases where you have more than one central atom. So, having a multiple bond is going to take up more space than a single bond. That's because we simply have more electrons that are centered around one area, and so that's going to increase the electron-electron repulsions. What that means then is that the bond angles that include the multiple bonds, so as indicated here on the right, these are larger, whereas the bond angles opposite the double bond are going to be smaller. You can think of it as the double bond is occupying more space. It squishes these elements closer to each other, which reduces the bond angle between them and increases the bond angle next to the double bond. However, you want to make sure that you account for resonance. Remember when we looked at resonance and we discussed how it equalizes bond lengths and bond strengths? Well, it turns out that it's also going to equalize bond angles. And the reason is because if you have, let's say, a scenario where let's call this X, Y, and Z. And let's say that we have resonance forms. That are all the same. What is if we look at this, the resonance form on the left, what would be the bond angle here? Well, we would expect it to be less than 120. However, if we look at it in this form, we would expect it to be greater than 120. And same thing here, we would expect it to be greater than 120. So it turns out that the resonance forms cancel each other out. And in the same way that the real structure is a melding and averaging of the resonance forms, the real bond angle is going to be depicted, as we've got here, our dotted lines indicating partial bonds. Our real bond angle is going to be exactly 120. All right, let's practice this. What is the bond angle A in nitrate? Pause the video and try this on your own. Welcome back. So, for nitrate, we have a steric number of 3. The electron domain geometry is trigonal planar. Molecular geometry is trigonal planar. However, we have that double bond. Normally, we would say that this bond angle is going to be greater than 120, and this would be less than 120 because of the extra space that that double bond occupies. However, we need to keep in mind that those bonds are the same because of resonance accommodations. Because they're the same, they repel each other equally, and thus the bond angles are going to be the same. Therefore, this is exactly 120 degrees. Now let's take a look at larger molecules, ones with multiple central atoms. You should be able to do this. So what I'd like you to do is to pause the video and try to determine the electron domain geometries of each central atom. Keeping in mind, all you need to do is focus on one atom at a time, and then you can evaluate how many domains does it have, what's the electron domain geometry based upon that. Something that you'll notice here, however, is not shown are the lone pairs of electrons. So this is good practice evaluating where will there be lone pairs of electrons. As a reminder, you'll want to evaluate this using the rules of valence. So look for how many bonds an element has, and then the remaining electrons must be supplied as lone pairs of electrons. Okay? All right, so pause the video and try this on your own. Determine the electron domain geometries of each of those central atoms. All right, so hopefully you were able to determine it. Let's see here. Nitrogen here should have a lone pair of electrons because it has 3 bonds. Oxygen here needs 2 sets of lone pairs. All of the other elements are satisfied. So what is the electron domain geometry of each of them? We have a tetrahedral electron domain geometry for that carbon atom. It is trigonal planar for this carbon atom because it has 3 electron domains. Trigonal pyramidal on this nitrogen. And this would be bent. Now, I've made a little mistake here. I've indicated the molecular geometries, which I did not ask you to do, but maybe you did instead, or in addition to. Electron domain geometries here, we still have tetrahedral, and here we have tetrahedral. There we go. Okay? The next thing that you should be able to do is determine the bond angles around each central atom. So what would be the bond angle for this carbon? Go ahead and try it and then come back. Did you figure it out? It should be exactly 109.5. This has 4 electron domains, and all 4 of those domains are bonds. Therefore, it will have its ideal angle. Okay, now pause the video and try to determine the bond angle for each of the other atoms that are indicated. So for the nitrogen to the so here, here, and then here. Welcome back. So for the nitrogen, we see again this has, remember, 4 domains, but 3 of them are bonds. That means it's going to be close to 109.5, but slightly less than, due to the increased repulsion of the lone pair of electrons. For the carbon in the ring, it has 3 electron domains. 3 of them are bonds. So it should be approximately 120 degrees. Now, you might look at this and say, well, okay, this bond angle is going to be larger than 120, and this one will be less than 120. But remember, as we've seen before, if there's resonance, then those cancel each other out. And this structure here, you might recognize as a benzene type structure. We could have drawn the double bonds instead of here, here, and here. We could have put them 1 over. And that is the other resonance structure. So it turns out that this all has exactly 120 degrees. Now, if you didn't quite get that this time, that's okay. This will take a little bit of practice. The last one for the oxygen, this has 4 electron domains. It has 2 bonds. Therefore, we know it's going to be close to 109.5, but it's going to be less than that. In fact, it will even be less than the angle for the nitrogen atom. And if we look at this molecule in 3 dimensions, we can see the fact that we do have some bent structures. This is trigonal planar, 120 degrees. We have tetrahedral, and we have a trigonal pyramidal electron or molecular geometry. That's it for this video. Thanks for watching. I hope you have a wonderful day.